Swayam Prabha. Digital India. Educated India.
Fan of CSK. CSK. No one is a fan of KKR? Why are you a fan of CSK? Thala only, right? How you became a Thala? Huh? How you became a Thala? How you captain? A cool captain. Okay, let's analyze more. A very calm, consistent person, right? He wants to know that action speaks louder than words. Okay, so all of you should follow that. Work hard, perform, and your performance will show. Okay. So what we are going to discuss today is a new subject which you may have heard a little bit by then. It will not be a very formal way of how people give a lecture. We will have a conversation, and through that conversation, we will learn about the subject. Is that fine? Okay. The subject that I thought I'd talk about is solid state physics, and that's a branch of solid state physics which is called electronic structure. What I am going to do in next 1.5 hours or so is that I'll tell you why this is such an important structure. Every gadget that we are using, its properties can be explained by something called electronics. Why something is a battery, why something is in electronics, why something is semiconductor. All these phenomena are defined by a branch of physics, but it's called electronic structure. So let's first understand solid, then we talk solid state physics. Right? All of you must have seen this phase diagram pretty much everywhere. With temperature, so you have three phases you kind of see, right? This is solid, this is gas, this is liquid. In fact, this is a critical point, a control point, right? And then another critical point where people talk about superfluid. Let us not bother about this part. It's not of our interest at the moment. We all know these three phases, right? So, this process of transition from one phase to another is called, in this case, what it is called? It is sublimation and it is deposition, right? This is vaporization and this is vaporization and condensation, right? This is freezing melting and freezing. This mechanisms your teacher must have taught you that, right? All of you. But what, and also all of you know about the mechanical behavior of it. For example, by now you must have heard about this kinetic theory of gases. Boyle's law, Charles law, Bernoulli's equation. For its that is called subject is called fluid mechanics, right? The fluid mechanics indeed covers this subject, the mechanical behavior. Okay, and of course for the solid state system you have done classical mechanics like fluid a ball, measuring its velocity, tracking its path. All these are classical mechanics phenomena that you look at on this side, and you look solid state, the fluid mechanics on this side. We are not going to talk any of them. What we are interested to see is that how the atoms and molecules behave in each of the group. Okay, so our interest lies in seeing how the atoms and molecules in these phases. So in gas, what do you see? The atoms or molecules. It can be a single atom or it can be a bunch of atoms. Am I correct? All single atoms will be separated from each other by a long distance. And all the single molecules will be separating from each other by a long distance. How large this distance would be, can you guess? Make a guess. Let me understand how you understand the length scale. Huh? Micrometer is too much. Nanometer. A few nanometer, 1 nanometer. So, few nanometers. Now, Professor Madras, I heard he taught you guys a bit of quantum mechanics. What did you learn in quantum mechanics? Eigenvalues, eigenvectors, Schrödinger equation, that's wonderful. Hamiltonian operator, all things you learn. Wow, that's interesting. Let's take one single example of what person understands. Hydrogen atom. Oh, this is going to move. Right, so in hydrogen atom, how many electrons you have? 1 electron. Okay, so you have 1 proton sitting at the center, right? Then you say 1 electron around, right? Proton, electron. Then how does your Hamiltonian look like? If you are heard Professor Madras, you must be knowing it. Right? It has a kinetic energy component. Did he write something like this? Did he write something like this? Little loud? Yes. It's a kinetic energy component acting on the wave function or what we call eigen function plus a potential energy component, right? Then, so you get E star. Is that correct? Then they say that you don't have only one eigenvector or eigenfunction, you have n number of eigenvector or eigenfunction. Corresponding to them, you have n number of eigenvalues. So, psi n, n, n1. Right? If you do the math correctly and if you solve this problem, you will find that your En is minus 13.646 by n square. Is it related or related? Right? N is equal to 1 is your ground state, the lowest energy state. Then 2 is your next excited state, next first, second, third, fourth. You go on like that. So if you draw the energy scale, so it will be E1, E2, E3, like right. So first one lies at minus 13.606 electron volt. The next one lies at 13.606 divided by 4. That is how much? 3 point something. So the difference between them is around 9 to 10 electron volt. It tells that these are very discrete, separate from each other, right? Now, if you say that I am not interested in hydrogen atom, I am interested in some other atom. Pick an atom of your choice. Which atom you like? You don't like any atom, okay? What? Oxygen, okay. You have oxygen. How many electrons does the oxygen have? 8 electrons, okay. So then it has 8 protons, and then what else? 8 neutrons. So you have proton plus neutron. Then you have to have around it 8 electrons. Am I correct? Now, when we wrote this expression, pay attention. What is this potential energy due to? Interaction between the electron and proton. This is the interaction between electron and proton. Correct? This interaction is called electrostatic interaction, the Coulomb interaction. The Coulomb's law defines that interaction. So that potential is governed by that. So we can say that electron proton, right? Or electron nucleus. Now when it comes to oxygen, how do you define how many kinetic energy operators you have? We are studying for electronic structure. By the way, when I say electronic structure, what does it mean? How does the electrons behave inside a system? Be it solid, be it liquid, be it gas. The motion of electron inside a system is broadly defined as electron structure because its motion is not very random. It is not very random. It is defined by certain principles, certain laws, certain invariances. Okay? So it is a very structured motion of electrons in the system, and that's why it is electronic structure. Okay, so what we are trying to understand first is the electronic structure of a single atom. Right, our job is to first to learn the electronic structure of a single atom, then the electronic structure of a molecule, and then the arrangement of atoms and molecules. Then we will slowly bring them to us. Then it will become electronic structure of a gas, electronic structure of a liquid, electronic structure of a solid. We'll stop. So first we will learn about the hydrogen atom. Your teacher was taught you already that there is one electron plus one proton. The interaction among them electron and proton or electron and nucleus in general, is it attractive or repulsive? It is attractive. That's why the electron is bound to the system, right? So now when we come to oxygen, you don't have only one electron. You have plenty of electrons, 8, right? So your Hamiltonian will have summation over I del I square. Pay attention. This I, all of you know how to use the summation in this. I stands for each electron. Not a single electron. There are 8 electrons, right? So there are each electron is small. Numeric. Correct. Now there are 8 kinetic energy operator in principle because there are 8 electrons you guys are talking about. Now there is a electron ion interaction. So each of the outer electrons, all these electrons, they will have an attractive interaction with the nucleus. This nucleus consists of 8 protons positively charged masses, right? So it will have p electron ion. Don't sleep. I have not started talking anything now. Okay. Plus. So this is electron ion. This is an attraction. Do the electrons love each other? They hate each other, right? They try to repel each other. Therefore, there is another term, electron. So there are 3 terms in your Hamiltonian operator. This operator what is called H side. This H is the operator acting on a wave function side, giving you the energy eigenvalue. So in this case, there will be a very competitive interacting component in the system. There is no, this is a single electron. One free electron living in an attractive potential, happy. Now in this case, one free electron doesn't live in attractive potential only. There are many electrons lives in that attractive potential. It's like if you have siblings, how many of you have siblings? All of you have siblings? How many of you have single child? So mama and papa attention goes to all of you 100%, right? And if you have siblings, you fight with each other to get mama and papa's attention, yes or no? You don't fight with each other? You fight with your brother and sister, yes or no? Why do you fight? Why do you fight? Because you want an attention from papa and mama, and your brother and sister also want attention. And you think that something goes little extra to one, then you have a fight with the other. You got extra, you got one additional pen, one additional chocolate or anything, so there is a fight. Imagine that particular fight is this electron and delay. Each electron wants the attention of the nucleus, but then all these electrons they fought with each other, and so many things they fought with each other. Then what they will be equilibrium, right? After fighting with each other, who will sleep on the left side of the bed, who will sleep on the right side of the bed, all this thing, right, brothers and sisters? So similarly, each electron will fight. Finally, their energy eigenstates and eigenvalues will be defined. Okay. Now we have, for each of the electrons, we have this eigenstates and eigenvalues. Okay. So instead of oxygen, we have new set of eigenstates and eigenvalues. Let me draw the picture here. After fighting with each other, after if you solve this Hamiltonian together, you won't have the eigenstate or eigenvalues as you saw for the case of hydrogen, because you have many electrons, they fought with each other. By the way, when one free particle is there, like in the case of hydrogen, you can solve it easily. When two of the free particles are there, still you can convince, you can solve it easily. Once you move beyond three particles, it is very difficult to solve in a piece of paper. The modern day computers, new theoretical phenomena, new approximation, you have to bring in to solve it. The best analogy is like this. If two friends, one friend is there, any incident happens, the credit of the blame goes to that person. If two of them there, either one has done the right thing or the other has done the right thing, or one has done the wrong thing or the other has done the wrong thing. Now if the three friends are there, imagine, this friend can say that I didn't do the mistake. These two have done the mistake. This can say that I didn't do the mistake, you two have done the mistake. Because that one uncertainty has come up in the system. So this uncertainty also happens in the case of electrons, many particles. Many particles, their interactions are so entangled that you cannot track each of them so precisely. Each of the interaction will be influenced by the rest of it. Okay. Now oxygen have that picture, so you have so many energy eigenstates, right? Some of them will be closed, something like that. I'm just putting a sketch, it is not to the perfect. Now once the energy eigenstates are built, the electron will start occupying. Right? So how will the electron will start occupying that? The lowest energy state will be occupied first, then the next, then the next, then the next. Okay? Now each state will be occupied by how many electrons? Why? Okay, you know about Pauli principle? Okay. So since all of you know, I can go to a little more. What it says is that two electrons cannot have identical quantum numbers. What are quantum numbers here? For a simplicity purpose, I wrote N only. Okay, but there are three quantum. Yes. So you have N, L, and N. Then there is MS. Yes. So your energy states should be defined as for N, L, M, and N. Right? Okay. Now what happens? is that you define your N is equal to, let's say, 1. L will be defined accordingly. What is L here? If N is equal to 1, L will be 0 because L goes from 0 to N minus 1 in this case. So L is equal to 0. Okay, to avoid your confusion, let's clean this part. So N is equal to 1, L is equal to 0. So M is equal to 0. So 1, 0, 0. Correct? Right. So this is the state you calculated from this Hamiltonian order. On top of it, electron has another quantum mechanics, and that is called spin. Okay, and this spin ms has two values. So plus h bar by 2 sigma minus h bar by 2 sigma. H bar by 2 is ignored. H bar is ignored. Mostly people write plus half minus half. Okay, so that is just plus h bar by 2 minus h bar by 2 sigma. So for this quantum number NLM, you have 1, 0, 0. Now you have two possibilities: 1, 0, 0 half, 1, 0, 0 minus. Therefore, two electrons can occupy. Because this half and this minus half make them two distinct quantum numbers. They are no longer identical quantum. Correct? So we occupy two electrons. How many electrons left? 6 electrons. So we'll go to the next energy state. So N is equal to 2, L is equal to, L has how many possibilities? So L can be 0 or 1. Okay, so you have 2, 0 in one case, 2, 1 in another case. When you have 2, 0 in one case, what is M? 0. And if you have 2, 1, then M can be? So minus 1, 0, plus 1. Correct? Okay. So next step we can define as 2, 0, 0, 2 half 2, 0, 0 minus. You have two spins. Okay. You got occupied 2 electrons. How many electrons left? Huh? We finished 2 electrons here, 2 electrons here. How many electrons left? 4 electrons. Am I correct? Okay. Now how to occupy those 4 electrons? Let's look at the next quantum number. That is N is equal to 2, L is equal to 1. I'll write a little more in detail. So N is equal to 2, M is equal to N is equal to 1. So M is equal to minus 1, 0, 1. Again, for minus 1, there are 2 possible spin quantum numbers. So plus half, minus half, plus half, minus half, plus half, minus half. So how many electrons you can occupy for N is equal to 2, L is equal to 1? 6 electrons you can occupy. So in fact there are 6 states. We can break into pieces. Correct? Okay. So where will these electrons go? Which electrons they will occupy? Which state they will occupy? Let's say these 2 represent this. These 2 represent this. These 2 represent this. Their energy are identical. You have a question? So their energy are same. When the energy are same, what term we use to describe the degenerate? Okay, very you guys are smart. Degenerate states, right? So the electron can occupy any of them. But this cell is not filled. Correct? So electron can stay here, 4 electrons can pick out of 6 states. 4 electrons can pick out of 6 states. So you can have this, you have done this permutation and combination, binomial theorem. Okay? Imagine 4 out of 6. So many configurations you can design. However, since these are empty, the atom doesn't stay grounded. Okay? The atom would like to fulfill, occupy this state so that it would be like an inner state. Okay? Had it been 10 electrons, like in this case 8 electrons, it could have been 10 electrons. Which one has 10 electrons? Neon. Had it been 10 electrons, these cells should have been filled. Okay. Once the states are filled, the entity in this case is atom, is inactive. Inactive. Okay. Once the states are filled, the energy states are occupied. The system is no longer volatile. It will occupy and stay happy. All demands are fulfilled. Right? You got all the toys. So all requirement is fulfilled. Now if this is not filled, this remains active. It is prone to act and react, what you call chemical bond. Okay? Therefore, you will never find single oxygen atom moving free. Have you seen any chemistry teacher has ever told you single oxygen atoms are moving freely? But all chemistry teachers have told you that all the neons move freely. You have single neon atoms, single argon atoms. You have a neon gas, argon gas, right? So, and that brings to something you might have understood, octet loop. Have you heard about it? All the cells are closed cells, right? Okay. Now imagine that these are empty, right? Then these are prone to react. Okay? When they are prone to react, then one oxygen will form a bond. Okay? Then these oxygens will share their interactions and they form a bond. I'm not going to produce the one. And that's how a oxygen molecule will be formed. If you remember this picture, you have either a single atom or a bunch of atoms forming forming a molecule. Okay. So when a bunch of atoms forming a molecule, the main reason that they form a molecule is to stay in a ground state. The whole effort has always been to stay in a ground. Okay. The energy will be lowered by forming a bond. If you have a single oxygen atom, its energy is not lowered. By bringing them close to each other, they form a bond, their energy is lowered and they stay together. Now, that's how you form single entities. Right? A single entity can be atom, like argon, neon, krypton, xenon, and all these things. You see their cells are filled. If their cells are not filled, they try to form a bond. Like hydrogen forms H2, oxygen forms O2, nitrogen forms N2. Then it can be hetero interactions like ammonia, NH3, am I correct? Water, H2O. They form their molecules, right? So, how does your H2O forms? OHS. Right? And your teacher must have told that two lone pair, then one electron from oxygen, another hydrogen, and oxygen, hydrogen plus. They form this body. So that's how a molecule is formed. Now what we have learned, when I write all these configurations, I am talking about the configuration of the electron structure of the atom. Or now I am going to talk about the electron structure of the molecule. Now if I try to find out the electronic structure of a molecule from quantum mechanics using the molecule gas, can you guys think about correction to this term? So this is a Hamiltonian operator we wrote for single atoms. In our case, oxygen atoms. We are bringing a molecule, one more oxygen. If we bring one more oxygen, how you correct this operator? You have to make a correction in this one. Because that is not a single nucleus or a single ion is there. There are two ions or two nucleus in there. In fact, I will come back to ion little later. Let's say nucleus right now. Nucleus 1 plus V electron nucleus 2. So this correction will improve the Hamiltonian operator, then you can calculate it. Without telling you guys that here I had written ion. What does it mean? To understand the concept of ion, let's borrow a small toy model that our famous scientist Niels Bohr had written. He said that your nucleus is around, electrons will move around it using the orbit. That's a semi-classical model or a semi-quantum mechanical model. Right? Now, this model is satisfied by these new quantum numbers, N, L, N. L defines the orbit. Okay? So, he said that the one with lower energy are more close to the nucleus. The one with higher energy are away from the nucleus and loosely bound to the nucleus. So, in this case, this 1s is more close to the nucleus. Then 2s, then 2p, then 3s, then 4p, like that. The more you move away from the nucleus, you are less likely attached to the nucleus. You are free to move. Okay? So from there, the concept of ion came into picture. Don't sleep. Alright. Don't sleep. Okay? So we can say that